what we talked about in the last section. uh, when you make a composite with thin laminates, you get typical composite thicknesses of the order of 1/16, 1/8, and things like that. More than 1/8 of an inch thick is typically not done, but there could be conditions where you could have very thick uh, composite samples or composite components. Curing becomes an issue when you increase the thickness, but so that's why you want to have, because you want to have less thickness, because most of the time the composite materials are non-conductive, both thermally and electrically. So passing the heat through in order to have uniform curing becomes an issue when you have very thick samples, very thick components. The most common one that you find, say, in the case of making boats and things like that, is the open mold process. So, you have only one side of the mold open. So, you kind of compress the uh, fabric and the matrix onto the mold. So the first one is obviously the hand layer process, where you first you apply a gel coat so that the side that is facing the mold will give you a very nice and clean surface. Then you can apply the fiberglass reinforcement through multiple ways, and the base resin mixed with the catalyst is then applied either by brushing or spraying and curing. The sprayer process could be either as a chopped fiber or as a strand rowing. It is fed by a chopper and spray gun, and it is deposited into the mold. Then you cure it at room temperature, and then you post cure it at elevated temperatures. That's typically what is done. The other common variety in composite fabrication is the vacuum bagging and autoclave and filament winding process. So we have a filament winder in our lab, so which you could come by and view the process to see what is going on here. So the vacuum bag is, you have a long thin sheet or pre-preg is laid on the table or laid on the mold. Then the sheet is cut and the laminate is constructed, and then you put it into a vacuum bag to remove the entrapped air, and it is cured in an autoclave or cured in an oven. In the case of filament winding, you have a fiber reinforcement fed through a resin bath, or you could also do it using a pre-preg, which already has some um, matrix around the fibers already, and it is done around a suitable mandrel, and the mandrel is cured and the molding part is stripped from the mandrel. The closed mold process means you have both sides of the mold present in there. So you are compressing the component using both sides of the mold. You can also do what is called an injection molding process. It is same as that in polymers, except that the fiber reinforcement is mixed with the resin, and it is a very highly automated and continuous molding process. And you can have continuous strand fiberglass or carbon fiber chopped and deposited on a layer of resin filler paste, and the sandwich is compacted and rolled into rolls or whatever. I mean, these are all different variations of variations of this process. Uh, if you have a rolled up sheet, made into a rolled up sheet, it is stored in a maturation room for 1 to 4 days, and then it is cut into proper size and pressed in a hot mold to form the final product. The advantage here is that it is a very efficient process. It's a pretty quick gives you good quality and uniformity. Sometimes you can even make parts within a couple of minutes, and you make these parts continuously one after the other. And this is a process used for making beams, channels, and pipes made out of composites. So it has to be a continuous process, it has to be a fast process, and it has to give you uniform quality. So sheet molding process is typically used for those kinds of applications. In the case of metals, you can have metal matrix composites. So you can have continuous fiber reinforced metal matrix composites, or you can also have chopped fiber metal matrix composites, which is typically used in the aerospace, auto industry, and sports goods type of applications. An example is shown here where you have an aluminum alloy boron fiber composite. The boron fiber is made by depositing boron vapor on a tungsten substrate. So if you really look at it, in the center you have a tungsten filament, and you have the aluminum matrix that is infused in between the fibers. And by incorporating these fibers, the tensile strength of aluminum, say 60, 61 type of material, which typically has a tensile strength of around 300 gigapascals, 300 megapascals, it can go up to 1.4 or 1.5 gigapascals. I'm sorry, there's a mistake here. It should be 310 megapascals to 1.4 gigapascals. The elastic modulus increases from 69, which is pretty low compared to steels, 69 to 231 gigapascals. So by incorporating these fibers, you are creating a composite material that has got typically properties that is equivalent or better than that of steels. The more common one is discontinuous fiber and particulate reinforced metal matrix composites, where you can have irregular shaped alumina and silicon carbide particulate are used, and it is mixed with molten aluminum and cast into ingots or billets. So you can have up to 20% silicon carbide, and the tensile strength increases from 310 to 496 megapascals, and the elastic modulus almost doubles. And the advantage is that the properties improves not just in strength and modulus, but it also increases tremendously for scratch hardness. So for example, if you are going to be making uh, aluminum piston, and you know that the aluminum piston over a period of time it wears out, so it improves the wear resistance by adding these discontinuous fiber or particulate reinforced um, materials like alumina and silicon carbide. The more exotic variety of composites are in the field of ceramics, and you have what are called ceramic matrix composites. And one thing to note here is this: in polymer matrix composites, why are you adding fibers? It's because you want to increase the tensile strength. But in the case of ceramic composites, you are adding fibers not just to increase the strength. I mean, sometimes you may not even increase the strength, but mainly to increase the toughness, that is, its resistance to cracking and resistance to failure. And you have two varieties again. You have continuous fiber reinforced ceramic matrix composites, and as I mentioned to you in the last class, you have one of the developers of the ceramic matrix composite that is used in the current Gen X GE Gen X engines. which are made out of silicon carbide, fiber reinforced silicon carbide. One of the developers, Dr. Raj Singh, he developed that while he was at GE Corporate Research Center in the early 1990s. So you can understand how long it has taken for us to get this material qualified and introduced into the marketplace. You can also have discontinuous and particulate reinforced CMCs. So ceramic matrix composites, the acronym is CMCs. Polymer matrix composites, the acronym is PMCs. And metal matrix composites, the acronym is MMCs. So again, in this case, the fracture toughness is significantly increased. And here you use uh, a process called hard isostatic pressing. So you make the component and you put it into a fluid medium like coking coal or just an inert gas, and you apply significantly high pressure. So it applies the pressure uniformly around this component and cures and consolidates this component. So to talk about composites, we want to understand why we are introducing fibers in the case of ceramics. And one of the most important reasons for introducing fibers in ceramics, you know that ceramics in general are pretty brittle. So if you drop it, it is going to shatter into 1,000 pieces. So